Okay, so here we are again talking about limits. And I know you're like, wait, we did limits back in Unit 7. Aren't we done with limits? The answer is obviously no, because all derivatives are really just evaluating a limit. I know you're like, wait, you're really testing my limits with these limits. So with that, we want to, again, recall how to evaluate limits to infinity and use descriptive limits. Fun fact, not dealing with limits though, did you know that all male goats are named Billy because they're male, and all female goats are called, I'm sorry, I shouldn't say named, they're called nanny goats because they're female? I don't know where that comes from. But my grandma, RIP, we called her nanny, but she wasn't a goat. Think about that. Okay, first problem. We are going to try to evaluate the limit as x goes to infinity of the quantity 6x minus 5x to the 7th over 3x to the 7th plus the quantity negative 8 over x plus 3 times the quantity 7 to the negative x minus 2. I want you to try this on your own. You should be able to do this. We've done this before. It may have been a while, but you have done this before. So I want you to think about it, pause the video, evaluate the limit, unpause when you are ready to check. Okay, so hopefully you got an answer of 10. So the limit as x goes to infinity of this whole quantity is 10. How do we come up with that? Great question. Well, so first we need to remember one of our properties of limits, and that is that if we are evaluating the limit of a product, then we can evaluate the product of each limit individually. So that's what I did here. So I just took each one of these quantities and evaluated the limit of each of them individually. So the first one, 6x minus 5x to the 7th over 3x to the 7th plus 10, that is a rational function. I recognize it's a rational function, so then I also looked at the degree of the numerator and the degree of the denominator. I noticed that those are the same. If they're the same, then I recall that it has a horizontal asymptote at y equals the ratio of the leading coefficients of the numerator over the denominator, which is negative 5 over 3. For the second quantity here, I actually turned it into a rational function with a common denominator. It is currently a rational function, but I got a common denominator so that I can see the degree of the numerator is the same as the degree of the denominator. Therefore, the ratio of the leading coefficients is 3 over 1, or y equals 3. So there's a horizontal asymptote at y equals 3. And then for the last quantity here, I recognize this is an exponential function, exponential decay to be exact, but that doesn't change the fact that it's an exponential function. So normally there's a horizontal asymptote at y equals 0, but this was shifted down 2, so it has a horizontal asymptote of y equals negative 2. So now if I was to evaluate the limit of each of these, I know that the limit is going to be the value of the horizontal asymptote, and so then I can multiply those together. So negative 5/3 times 3 times negative 2 is positive 10. Therefore, our limit is 10. Any questions? Great. Moving on. Next one. Try this on your own. These are the problems that you really didn't like before, because I actually want you to show me some work. So I want you to evaluate the limit as x goes to negative infinity of the quantity 3x minus 2 over the square root of the quantity 2x squared plus 1. Pause the video, unpause when you're ready to check. Okay, so here we should end up with negative 3 over the square root of 2. How do we come up with that? Excellent question. Well, here's some little work, but let's look at the top, because that's where we want to start. Start at the top. That's what I always say. So first we want to recognize we are evaluating the limit as x goes to negative infinity. This is not a rational function, so we cannot just use our rules of horizontal asymptotes for rational functions. It's close, but not exactly. So what we first want to do is we want to say, okay, well, since x is going to negative infinity, I'm going to let the square root of x squared equals negative x. Why can I do that? Great question. Well, remember that actually the square root of x squared is the absolute value of x, so therefore it equals x and negative x. But if x is going to negative infinity, then I can say it represents negative x. Great. Why do I care about that? Well, because I need to do a little bit of algebra, so I need to multiply the numerator and denominator by the same thing. But what is that thing? That thing is 1 over the square root of x squared. The reason why I need to do that is I need to be able to get something inside of the square root here, and the only way to get something inside of a square root is if it has a square root itself. So the denominator, I multiply by 1 over the square root of x squared, and that allows me to rewrite the denominator as the square root of 2x squared over x squared plus 1 over x squared. But in the numerator, yes, I am multiplying by 1 over the square root of x squared, but remember, up here, I said that the square root of x squared is negative x. So since the numerator doesn't have a root, instead of writing 3x over the square root of x squared, I'm just going to write 3x over negative x, and then minus 2 over negative x. Because again, up here, I defined the square root of x squared as negative x. So now I simplify a little bit. The x is here reduced, and this is negative 3. Let's just say it becomes plus 2 over x. In the denominator, the square root of 2 plus 1 over x squared. Now I can evaluate the limit. If this is a negative infinity, this term goes to 0, this term goes to 0, so I'm left with negative 3 over root 2. Excellent. Okay, so now in the next section here, there are 8 different graphs. I want you to do all 8 of these. There are many correct answers for all of them. I'll show you a couple of correct answers when we go through this. But basically, you are trying to graph a nonlinear function, so it can't just be a straight line, with the following limit examples. So again, there are many correct answers. So the first one, the limit as x goes to 2 of f of x equals negative 1. So you're just graphing any function as long as it's a nonlinear function that has this limit. So pause the video, do all 8 of these, and unpause when you're ready to check. Okay, so here are 2 examples I did for the limit as x goes to 2 of f of x equals negative 1. So here I just drew some kind of polynomial looking function, and I just made it a continuous function, so it's because it's polynomial. So when x is 2, y is negative 1, therefore the limit as x goes to 2 of f of x equals negative 1. Here I drew a different function, and I made a hole at the point 2, negative 1, but it still has a limit as x goes to 2, the limit is negative 1. Again, many other correct answers. Here we're evaluating the limit as x goes to infinity of f of x also equals infinity. So the first thing I did was sort of like an exponential growth function. So as x goes to infinity, y goes to infinity. Here, a parabola. As x goes to infinity, y goes to infinity. Here, a rational function with a slant asymptote. So as x goes to infinity, y goes to infinity. Again, many, many correct answers. Next one, we're doing the limit as x goes to infinity of f of x equals 3. So what needs to happen here is we probably need a horizontal asymptote at y equals 3, because remember, as x goes to infinity, that's talking about end behavior. That's also why we're bringing limits back right now. But if the limit is a constant, then I need a horizontal asymptote at y equals 3, because I'm doing only nonlinear functions. So for instance, I can't just draw the line y equals 3, which would also have a limit as x goes to infinity of 3, but that would be a linear function. So here I drew some rational function that has a horizontal asymptote of 3. Here I drew like an exponential decay function that was shifted up 3. So those are just 2 examples. Next one. Here the limit as x goes to negative infinity of f of x equals 2. So again, I need a horizontal asymptote at y equals 2 in order to have a limit as x goes to infinity or negative infinity be 2. So here I drew an exponential growth function with a vertical shift of 2, so that as x goes to negative infinity, the horizontal asymptote is y equals 2, which means the limit is 2. Here I drew a rational function with a horizontal asymptote of 2. So again, as x goes to negative infinity, the function approaches a y value of 2. Similar sort of idea, the limit as x goes to negative infinity of f of x equals 0. Same thing, except for this time it just doesn't have a vertical shift. So exponential growth function as x goes to negative infinity, y, or the limit, approaches 0. Here, rational function with a horizontal asymptote of y equals 0. So as x goes to negative infinity, the limit, or y, values approach 0. Next one, we're doing the limit as x goes to infinity of f of x equals negative infinity. So that means as the graph goes to the right, it has to go down. So the first example here, I drew a rational function with a slant asymptote. So as the function goes towards the right, it is going down to negative infinity. And here I drew an exponential growth function, but with a reflection. So if you multiply the whole function by a negative 1, so this would be like negative e to the x or something. So then I can see as x goes to infinity, y goes to negative infinity. All right, two more of these. So the limit as x goes to 2 from the right of f of x equals negative infinity. So what I did, I drew a vertical asymptote at x equals 2, and I made it so that as x approaches 2 from the right, the function is going down towards negative infinity. So I drew a rational function with a vertical asymptote at 2, and this piece going down from the right-hand side. I also could do like a log graph. So here I said it's the natural log, could be any log base, it doesn't matter. And it's shifted 2 to the right. So again, the vertical asymptote is at x equals 2. So as x approaches 2 from the right, the function is going down towards negative infinity. And then here, the limit as x goes to 2 from the left of f of x equals infinity. So I can do that same rational function I did before, but now as I approach 2 from the left, the function is going up to infinity. And here I have a sort of log reflection graph where I have a vertical asymptote again at x equals 2. And as I approach 2 from the left, the y values are going towards infinity. Okay, again, on all of those are many correct answers, so if you're not sure if what you did was correct, please just check with me tomorrow in class. All right, last problem. I want you to do this on your own. Evaluate the limit as x goes to infinity of 2x squared minus 4x over x plus 1. Pause the video, unpause when you're ready to check. Okay, so hopefully you got infinity as your answer. So we have a descriptive limit. Remember, technically the limit does not exist, but our describer is that it is going towards infinity. How do we come up with that? Great question. Well, this is a rational function again. I notice the degree of the numerator is greater than the degree of the denominator. So what I wanted to do then was I wanted to find the oblique, or in this case, slant asymptote. So I did synthetic division, and I end up with 2 and negative 6, which means that I have a slant or oblique asymptote with the function y equals 2x minus 6. So then I can just think about, okay, well, this is a positive slope, so I can picture what does a positive slope look like. It looks like this, so I know as x goes to infinity, y also goes to infinity. Or I could just say, well, evaluate the limit as x goes to infinity of 2x minus 6, and that equals infinity. So therefore, the limit as x goes to infinity of 2x squared minus 4x over the quantity x plus 1 also has to equal infinity, because the slant asymptote describes the end behavior, and a limit as x goes to infinity is asking for end behavior. Any questions on anything? Okay. So what do we care about? We want to continue to understand how to evaluate limits to infinity and infinite limits as well. Remember that the limits as x goes to infinity are describing end behavior. And so that's why we're bringing this back now, because we're talking about end behavior with all of these different functions and graphs. And we also don't want to forget about limits, because they are the basis of everything else we have been doing this semester, because all derivatives are actually from limits. So good talk.